for the invitation to give this series of lectures. This is a very, I think, I really like these kind of events where even though the event is somehow rather topical, it's also mixed. So there is a kind of mixed audience between homotopy theorists and representation theorists in this case. So just to orient myself, I want to start with a show of hands. So who thinks they are more on the representation theory side? Okay. And the complement and the homotopy theory side, is that right? Yeah? Very good. So more or less what I expected. So this series of lectures is about something that we call the Derived Auslander Iyama Correspondence. So this is a joint work with my collaborator Fernando Muro from Sevilla, who actually established this correspondence in what we will come to call in the series of lectures the case D equals to 1. This will become more meaningful later. And instead of starting with a plan of the lecture series, so as it turns out, this Derived Auslander Iyama Correspondence is a theorem of a type that maybe, except the people that have already heard me speak about this, maybe you have not seen necessarily this kind of theorem. So it will take me too long to sort of try to make a plan that makes sense with regards to what the correspondence actually is and so on. So instead what I will do is I will start with some motivation. So this motivation will take us maybe some time. And in fact, will have nothing to do at the beginning with any sort of higher structures. And I think this is one of the interesting things about this result that I'm going to talk about, that in the end, to solve it, you do need to use, as far as we know up to now, methods of homotopy theory. Okay? So throughout, we will work over a base field K. We will be interested in finite dimensional K algebras. So everything that we do will be linear over this ground field K. We will also be interested in the category, rather K-linear category, of finite dimensional, say right, this is just some convention, lambda modules. We'll also introduce some more notation that will be useful later on. We will write small approach lambda for the category of finite dimensional right projective lambda modules. This is of course the full subcategory of the category of all finite dimensional right lambda modules. And we will also be interested a little bit in the category of injective lambda modules. So everything we do today will be finite dimensional. So whenever I say algebra or module, I always mean finite dimensional in case I don't say that explicitly. So there is also an important duality. There is a duality between the category of finite dimensional right modules over lambda and the category of finite dimensional left modules, given by taking the K-linear dual of a module. So that's a basic duality that one has in the theory, and we will also need the notation. I will just write it explicitly since we're homological, it already appeared in Sierra's talk. So given a finite dimensional lambda module, we will write at lambda for the smallest full subcategory of mod lambda containing M and which is closed under the formation of finite direct sums.
At lambda, I think maybe at
Oh, so at M, thank you. At M. Is it correct now? Yes, thank you. At M, the smallest full subcategory of mod lambda containing M and which is closed under the formation of finite direct sums and taking direct summands equivalently that is also closed under retracts. Okay? So for example, Roch lambda is the additive closure of the regular representation of lambda, and the injective lambda modules are given by the additive closure of the dual of the regular representation of lambda under these dualities, or the dual of the projectives become injective, and all injectives are obtained as retracts of finite direct sums of such things. Okay? Yes. So classically, so meaning in around.
I don't really know what documentation lambda means.
It's it means lambda as a left module. So that because I'm working always in right module, so it specifies in right module. Yeah. So yeah. So the field of representation theory of finite dimensional algebras is rather young. It started around the 1970s. And at that time, people were very much interested in what are called finite dimensional algebras of finite representation type. Representation. So we say that lambda has finite representation type if there exists a finite dimensional lambda module such that the additive closure of M in mod lambda is in fact the whole category of finite dimensional lambda modules. So the category of finite dimensional lambda modules is a Krull-Schmidt category. So every module decomposes as a finite direct sum of indecomposable modules in such a way that this decomposition is essentially unique to reordering of the factors. And from that it follows that categories of this form are uniquely determined by the indecomposable direct summands of the module. So what this says is that every finite dimensional lambda module for a finite dimensional algebra finite representation type is obtained from a fixed number of finite indecomposable lambda modules. Yeah, so that's why the name finite representation type, because M itself has only finitely many indecomposable direct sums. So in this case, we call such an M an additive generator or a representation generator of the category of lambda modules. And such an additive generator by the Krull-Schmidt theorem is essentially unique up to multiplicity of its indecomposable direct summands. Okay? So as an example, as I assume that many of you were not necessarily previously interested in representation theory of finite dimensional algebras, maybe not even after what I'm going to say, but we will see. So there is a classical theorem, let's attribute it to Gabriel, that says that if Q is a finite acyclic quiver, then the path algebra of this quiver, so you can view a quiver, so a quiver freely generates a category by taking formal compositions of its arrows, and you can then k-linearize this because the quiver is finite. You can add all of that together into a single algebra called the path algebra of the quiver. This is of finite representation type if and only if Q is a dinking quiver of type A, D, or E, so meaning that the underlying undirected graph of Q is a simply laced dinking diagram. So this produces examples of finite type algebra. So we have seen today both in David's and Zira's talks, path algebras of n quivers, at least for n equals to 2 and to 3. And you saw that in those cases you can write a finite picture that's supposed to give you some kind of X-ray of your module category, which is called the Auslander quiver. Well, of course, these have the particular feature of being hereditary of global dimension 1. There are many more finite dimensional algebras that are of finite type, and in some sense they are unclassifiable. Yeah? So one can try to understand them in a different way. Now for this, we need a definition due to Tachikawa. So as you can see, this is all quite classical, right? So this definition from the 60s. So consider a minimal injective co-resolution so this is a minimal injective co-resolution of lambda viewed as a module over itself. So minimal means each of the terms of the co-resolution is an injective envelope of the corresponding previous co-kernel. So in a way, this means that this, as a complex, has no, let's say, additional redundant direct summands. Yeah, that's a way to understand what this means. So Tachikawa defined a certain homological dimension associated to a finite dimensional algebra called the dominant dimension. So, and the easiest way to write, so the dominant dimension of lambda is the smallest n such that In is not projective and infinity if not such n exists. So of course I could define it using infima and so on, but the easiest way to not get confused is just write explicitly what you mean. So it's a bit strange. So this resolution is in principle consisting, of course, of injective lambda modules. So I'm just supposed to count how many of them happen to also be projective. Maybe none of them, maybe the first few, and then I call that number of the first few the dominant dimension. And if no such n exists, so that means they're all also projective, then I say that the algebra has infinite dominant dimension. Okay? So there is a something is wrong with the year. Maybe the year is not correct. Well, let's maybe the years, maybe I took the wrong paper of Tachikawa. So there is a conjecture, so that you get an idea of why such dominant dimension could be interesting, called the Iyama conjecture, which says, so this is a very old conjecture, from around that time, that says the following: the finite dimensional algebra lambda is self-injective, meaning, in short, that the classes of projectives and injectives lambda modules coincide, if and only if the dominant dimension of lambda is infinity. And in fact, in the self-injective case, then the minimal injective co-resolution of lambda, because lambda is already injected, consists just of lambda again, and then 0, 0, 0, 0, 0, 0, 0 as infinitum, and 0 is of course also projective. Yeah? So the statement is that if this number is infinity, then everything collapses and you just have the beginning of the resolution. So this conjecture is still open, and there is, some of it depends how you measure progress towards solving an unsolved conjecture, so there is of course progress, but in some sense it's still, I would describe it as wide open. So, yeah, so this is maybe from 1958. I hope now I'm doubting my dates, but take those dates with a grain of salt. But the point is, you should regard this as it's an old conjecture. Okay? Now, well, one could try then to understand the behavior of algebras of increasingly large dominant dimension. Yeah? So maybe one's interested in this conjecture, we cannot solve it yet, so maybe one can try to understand algebras of increasingly large dominant dimension, but still finite. And one is also simultaneously motivated by the study of finite type representation, finite dimensional algebras. And there one has the following theorem of Auslander from 1971. So Gabel's theorem and Auslander's theorem, they are considered some of the seminal theorems in the representation theory of finite dimensional algebras. And this theorem says that there is a one-to-one correspondence between, so can you see there, if I write on the bottom of the blackboard? Yes? Okay. So Morita equivalence classes of finite dimensional algebras equivalence, and a different class of finite dimensional algebras, which are the so-called Auslander algebras. So these are algebras whose global dimension is at most 2, and its dominant dimension is at least 2, also up to Morita equivalence. So to go from top to bottom, what you do is you take lambda and you send it to the endomorphism algebra of an additive generator of the category of finite dimensional lambda modules that exist by virtue of lambda being a finite representation type. So yeah, I think this is a beautiful theorem because it brought a new point of view to representation theory of finite dimensional algebras, namely, so the kind of slogan that is repeated, always when this theorem is presented, maybe for the first time to people, is that it translates a representation theoretic property of the algebra lambda into a homological property of the endomorphism algebra of an additive generator. So this is somehow, maybe nowadays you could think, okay, yes, you should of course take endomorphism algebras of objects and try to understand that, but at some point we needed to understand these things for the first time. So this is actually a very insightful theorem because it led, for example, to the discovery of what is called Auslander writing theory, or the introduction of Auslander writing theory. By looking at this, for example, you might, this is a gamma. Yeah, that makes more sense. So in the critical case for the simple modulus over gamma of projective dimension 2, you could try to see what this means in terms of the representation theory of lambda, for example. So you could look at resolutions of simples for gamma and relate them to those of lambda, and then there's some interesting interplay that led to the developing of one of the main tools in the field. Okay, so this is all very classical. As I said, in some sense, these two sets are in bijection, and none of them can probably be understood completely, but it gives us some perspective.
Do you have like a one sentence, like for what dominant dimension gives you, kind of, what does it mean, like?
It's related to the existence of injective co-presentation in the category of finite dimensional lambda models. Yeah? So it has to do with the existence of enough injectives. Yeah? This is maybe a sentence that one could say. So don't worry too much about it. So actually, very soon we will depart from dominant dimension. This is really all for motivation. So we actually want to later understand this in a different context where it turns out this is not what turns out to play any role. But anyway, nonetheless, this is some fundamental theorem in representation theory of finite dimensional algebras.
Can you give a simple example of gamma?
Of gamma? Let me put it here. So if you put lambda, the path algebra of A3, then gamma is the path algebra of the following quiver with these relations. So we have seen that this is a picture of the indecomposable lambda modules, both in David and Sierra's talk. And what this is telling me is I just should look at this subcategory as an algebra, or just as a category if you want. Yeah, if you want to consider this as a category instead, so algebra with many objects instead of as an actual algebra is also okay. And in fact, this is how this generalization came about, because then you can consider the module category itself as an algebra with many objects and use these insights to develop some theory. So yeah, this is a basic example. Thank you for the question.
Okay, so sorry, maybe like does self-injectivity translate to self-injectivity of gamma?
No, gamma always has bounded.
But if I assume gamma is self-injective, then does it translate to some property?
No. So if gamma is self-injective, the module category is always abelian. So in a certain sense, it always has finite global dimension because So if you try to work out what resolutions, projective resolutions are coming from, they come from taking. I mean, you can get them by taking kernels. So existence of kernels is related to boundedness of the global dimension of mod lambda. Yeah? So abelian categories as algebras with many objects always have finite global dimension, independent if it's even if it's the category of modules over a self-injected algebra. Yeah. Yes. So right. So here comes something perhaps surprising. So for the longest time, it seems nobody wondered about moving this number. Yeah? So I tried to motivate this by the Nakayama conjecture to say, well, what about if you try to look at algebras of increasingly large dominant dimension, and maybe if you impose an additional condition, maybe you can say something, like for example, something of this kind, right? So, yeah, surprisingly, nobody asked about this for a really long time. So, before stating the result, let me give a definition, which is due to Osamu Iyama, which is that a finite dimensional lambda module is D cluster tilting for some D bigger than or equal to 1, so this is going to go to the D equals to 1 case that I mentioned beginning of the talk. So D is D cluster tilting, so if the following statements hold. So by the way, before there is any maybe potential confusion, this name is some kind of consequence of the history of the concept on the moment it appeared. It does not necessarily have a relationship with the theory of cluster algebras, for example. Yeah? But nonetheless. So M is D cluster tilting, we will abbreviate DCT, if we can describe the additive closure, this is called the additive closure of N, in the following two ways. It consists of the finite dimensional lambda modules that have no extensions by n in degrees that are strictly between 0 and d. And at the same time, it can be described as the full subcategory of those lambda modules that in the same range do not extend n.
You mean a y?
Y here, thank you. I change from x to y from one line to the other. Is that right? No? Thank you. So remark, if I put d equals to 1, there are no integers strictly between 0 and 1, so this condition is empty, so satisfied by every module. So every module lies in the additive closure of n, so this is cluster tilting, so one cluster tilting for d equals to 1 is the same as an additive generator. Okay? And something interesting already about this definition is that, well, it generalizes the notion of an additive generator, but it generalizes it from an empty condition. Yeah? So you generalize the empty condition to something that maybe is interesting. So this is already insightful, I would say. Yeah, it's not, there is a lot of freedom in which direction to generalize an empty condition. Yeah? But nonetheless, well, this is the definition.
Why does the generator?
In which case?
In the degenerate case.
D equals to 1, because every x satisfies this trivially because there are no conditions to be checked, so every x is actually inside here. Thank you. Good question. So the theorem of Iyama that generalizes Auslander's correspondence, so that's the Auslander correspondence, is what I nowadays like to call the Auslander Iyama Correspondence. I have 10 minutes.
So can you lift up the blackboard?
Lift more this blackboard.
The one in the back. Sorry.
You want to lift more? Sorry. This all the way to the top. Okay. Is that better? Notice that this is not the right. Yeah, this is the Auslander Iyama Correspondence. You have to, well, Auslander, let me do it like this. This is for d equals to 1, and here d greater than or equal to 2. Yeah? 1971 and 2000. So there is a 1-to-1 correspondence between pairs lambda comma n, where n is a finite dimensional lambda module that is D cluster tilting, up to some notion of equivalence that one could also in a suitable way reduce to a form of Morita equivalence. So I don't want to explain what this is exactly, it's not important, this is just motivation. And finite dimensional algebras gamma such that the global dimension of gamma is at most d plus 1 and at least, in the dominant dimensions at least d. Automorphic types. And it's given in the same way, so you take the pair lambda comma n to the endomorphism algebra. So, yeah, as an example, there is a certain, let me see if I get that right. There is a certain three-dimensional generalization of this picture that fits within that setting of algebras gamma for d equals to 2 and d plus 1 equals to 3. Yeah? So as I said, yeah, so this is an interesting insight of Iyama that he understood what happens if you, so the way, so Iyama was, by the way, for those that most people probably don't know, he was my doctoral advisor, so I have some insight on what he was thinking a little bit, because I asked him many questions all the time. So, yeah, of course, the way one gets into this concept is that by trying to reverse engineer Auslander's proof with this alternative assumption, right? And this is what led. So you find this definition sort of unmotivated, right? It's a bit maybe unusual thing to ask. Well, this is what makes this theorem true. Yeah? So this is one motivation for introducing this definition. So this is one of the many things that, as I understand, Iyama had in mind. In addition, things like the dominant dimension. Yeah? So try to understand the behavior of algebras of increasingly large dominant dimension.
Can you say something about how to go up?
It's essentially by taking the morphism algebra of the projective injectors. Yeah, the way you prove it is you use a trick, but it's essentially given by that. Yeah.
And then M would be the sum of all vector injectors?
No, they're all projectors. So this is like by Yoneda, M becomes projective, something like this. This is some kind of related to Yoneda orbit. So you can think of this as the indecomposable direct summands of M. You can think of as the representables associated to those indecomposable lambda modules. Okay. Yes. Sorry, but I lost my train of thought. Yeah, sorry. Yes. Okay. Right. So that's all I wanted to say about the classical story. So these stories, they call it classical because it happens in the context of module categories. Yeah? So I explained how this correspondence had something to do with the fact that the module category is abelian with some additional properties like enough injectives and things like this. And you can also introduce a definition of what is called, so it's something I did in my thesis called a d-abelian category, so some modification of the axioms of abelian categories that make it such that the additive closure of a D-cluster tilting module is the abelian. So you can think of this as some kind of abelian category story. Yeah, so this is some abelian category story. So what I want to talk about, the title happens to still be there, is about the derived Auslander Iyama correspondence. Okay? So I want to understand a statement of this kind in the context of triangulated categories, and as we will see, with enhancements. This will be essential for what we're going to do later. Yes. is the previous. So the next section is titled D-set closer tilting objects and twisted periodicity. So now we will sort of change completely the setup, or yeah, sort of, in some sense. So T is going to be an essentially small K-linear, confinite, Schmidt, which in this context is equivalent to an important complete triangulated category. And I'm going to introduce a straightforward generalization of the concept of cluster tilting module that it will turn out to be a classical generator of this category. So this definition is due to Iyama and Yoshino. And well, with the modification, so the importance of the small modification that we will present right now, heavily influenced by work of Keller and Opperman. So we say that an object T in my triangulated category T is this, let's say for simplicity that it is basic. Basic means that when I decompose T as a finite direct softened and decomposable summands, there are no repetitions among these summands. So I just take those summands that are really essential and the rules I throw away, because I'm typically interested in this additive closures. This is a harmless operation, but it simplifies some statements. So T is basic. Then we say that T is a D-set cluster tilting object, abbreviated DZCT, if T is isomorphic to its default shift, of course, in the triangulated category T, and the additive closure of T, and now there should be no, so of course the definition of additive closure applies it to T with the same definition, and it's the same definition, yeah? So I just write now quickly. So extensions in the triangulated settings are morphisms to the shift. So I just write the same definition. So this is a mixed here some symbols, X and T, T and Y. Okay. Yeah, so the rest is the same definition. So as I mentioned, the modification that is motivated by the work of Keller and Opperman is asking this additional symmetry. Yeah, so T should be isomorphic to its default shift. Now, in order to motivate this definition a little bit more, so by the way, this is the main definition that we will be interested in this series of lectures. Yeah? So this project, in a nutshell, is about understanding more about about D-set cluster tilting objects in general.
So, are those two conditions equivalent? Homs from and homs to them, or are they both conditions?
No, they're both conditions, just like in this case. Yeah? Under suitable Calabi Yau assumptions, you can take on one or something like this, but in general, you need to have these two conditions. So it's a very kind of symmetric motion. It's very strong. I mean, it's a priori. So we will see. I think I will want to, depending on the time, wait for mentioning examples either towards the end of the talk or at the beginning of next talk. for now I want to make some comments. So the same remark as before applies. For d equals to 1, we have that one set cluster tilting is the same as an additive generator of t. Because again, the so-called cluster tilting condition, so this vanishing of extensions is empty. So every object of t lies in the additive closure of this distinguished object. And using the fact that this object is already basic and that the suspension functor needs to permute in decomposable object, you can check that this isomorphism is needed. Yeah? So because these are the indecomposable summands of t are essentially all objects that you have that are indecomposable. So you can check this quite easily. So we get again a generalization of the notion of an additive generator. Then I will need to state the next proposition. I need some more notation. Given two full subcategories x, y, and t, I'm going to write x star y for the full subcategory consisting of all the objects in T that are extensions in the triangulated setting of, let me see the space here in the different direction, of objects in X and in Y. This operation is associative as a consequence of the octahedral axiom. So it's a convenient way to quickly talk about objects that are extensions of other objects. And the proposition of Iyama and Yoshino, that's in paper, is the following, is that T can be written down as the additive closure of T star, the additive closure of T shifted by 1, star, the additive closure of T shifted by B minus 1. I'll explain what this means, what this unravels to in a second. But notice that for D equals to 1, I get here 0, so I just recover the statement that additive closure of T is the whole ambient triangulated category. And now here comes something that maybe for those of you that are interested in triangulated categories and their enhanced variance is perhaps more, maybe we'll maybe look that this, maybe the definition does something very special. This means that for any object in T, there exists T0, T1, D minus 1 in the additive closure of T, so retracts or finite direct sums of copies of T. And the diagram X T0 something. So there is a resolution in the sense of triangulated categories in the most naive sense, so spliced triangles without any shifts. So these shifts appear by rotating the triangles, but if one writes the statement in this way, so there is a resolution in the sense of triangulated category. So this means that whenever you have a triangulated category with a dz cluster tilting object, you have access to finite resolution. So this property immediately implies that phi of T, that's here defined, is the ambient category T, but actually T generates in a very regular way. So I can write every object in terms of a resolution of objects in T of maximum length, yeah, D minus, so depends how you count it, like D minus 1, so D objects, yeah, without any shifts. So this is quite surprising. Yeah? So this is not very, yeah, it's maybe kind of extraordinary in the sense it's not very ordinary. Okay. Now, I have until past, is that right? Yes? Okay, thank you. So, according to the previous philosophy, in order to understand certain special kind of object in an ambient category, a possible strategy, if I want to follow this philosophy, is to look at the endomorphism algebras, yeah? And try to determine whether these endomorphism algebras have some special properties or structure that is not enjoyed by, say, an arbitrary finite dimensional algebra. For example, this is the case here, that endomorphism algebras of modules that are D-cluster tilting necessarily belong to this class of algebras. Yeah? So this is what we are going to right now, and this is this second part of the title of the section of twisted periodicity. So,
sorry, can I ask a question? This property about the extensions, do you need the object to be PZ cluster tilting, or does it also hold for just cluster tilting and then maybe some assumptions on the category?
this also holds for yeah, for D-cluster tilting. Yeah, you can always resolve in this way.
What does the T is? Like it's not necessarily that T is cluster.
Sorry, what?
So the number D that appears in this equation, like is it the
Sorry, here T is this cluster tilting. Sorry. Yes, take it. So I have a very nice kind of generator, and now I want to look at the endomorphism algebras. So for that, I will need some definitions. So if lambda, so the endomorphism algebra of T, my object, will be finite dimensional because my ambient category has finite dimensional home spaces. That's what home finite meant. I didn't say, but they have come up in the previous two talks. So if I'm given a finite dimensional algebra and an algebra automorphism, we say that lambda is twisted D plus 2 periodic with respect to sigma, if I need to make reference to this explicit automorphism, if the condition is the following. So I can view lambda as a bimodule over itself, by multiplication, of course. So I write lambda E for the algebra whose right modules are the lambda bimodules, just for simplicity of the notation. And I can take this D plus second CCG as a bimodule. And I ask that this is isomorphic to the bimodule lambda, where the action on the right is twisted by the given automorphism sigma in the category of stable lambda bimodule. So obtained by basically killing all projective modules. Yeah? So up to projective summations if you want. You can understand the statement like this. Yeah? So periodicity would mean that lambda as a bimodule is actually already isomorphic without twisting to this D plus second bimodule CCG, and the twisting is now this reference. Yeah?
Sorry, can you push up the high board?
The backboard, yes, sorry, I don't remember that this was much more technical. So, so now from now on, that's because one needs, so we work over a perfect field. This is just a technical condition that tells me that working with bimodules and simple modules and global dimensions behaves well in conjunction. For example, you can take K characteristic 0 or algebraical closed if you're happy with that. From now on, K is a perfect field. Then there is a theorem of, well, let me write in this way. So for a finite dimensional algebra, the following are equivalent. 1, lambda is twisted b plus 2 periodic with respect to some automorphism, algebra automorphism of lambda, and 2, the category of finite dimensional projective lambda modules admits the structure of a b plus 2 angulated category. So because of time reasons, I will not tell you what a b plus 2 angulated category means. This is a suitable modification of the notion of a triangulated category introduced by Guys, Keller, and Opperman in that 2013 paper. So basically it means that there is a class of sequences with d plus 2 terms and a suitable automorphism that plays the role of the shift that satisfies some axioms very similar of those of triangulated categories, and in fact triangulated is the same as triangulated. Yeah. So in the case d equals to 1, we're looking at triangulated categories. Yeah. So one direction from top to bottom, if you have a twisted d plus 2 periodic algebra, this is work of Claire Amiot, and in the case d equals to 1, and Lin in 2019. In general, the converse here is due to Hanihara for d equals to 1, and to Fernando and myself, but this part is now just is easy. Given the rest is just understanding that the proof extends to the general case. Yeah? So, yeah, so I mentioned this notion is in the case of, in the sense of Guys, Keller, Opperman. Okay, so that's interesting. Maybe some warnings is that the proof of the converse doesn't tell you that, so the proofs, they don't tell you that if you have a triangulated category, let's say triangulated category structure in the sense of Amiot, then it doesn't tell you that a triangulated category structure on Proch lambda comes from Amiot's construction. That's what I want to say. Yeah? That's what this doesn't tell you. It's just about the existence of this thing. So this is close to some kind of, Auslander Iyama type correspondence, in the sense it relates some derived analog of the concept of abelian category, like triangulated or higher angulated, to some properties of some algebras. Yeah? But
how do you produce the required sigma, assuming 2?
From where to where?
From 2 to 1?
From 2 to 1? Yes, so we can assume that lambda is basic, for example, for simplicity, and you have your sigma, and then you will be able to write this as twisted bimodule by some general theory. So it's that one. Yeah, as maybe I should have said. Yeah, let's actually assume this here. I have this in the mind all the time. Yeah. So you can write this automorphism as a twisted bimodule. Yeah, let me just keep it like this. Okay. Okay, so I have just a couple of minutes, so I will tell you maybe a couple of very short things. Sorry, yes. Tensor product over lambda. Thank you. Yes, so there is a theorem, more general than this, of Guys, Keller, and Opperman. That says if T is this at closer tilting, then the additive closure of T together with the default suspension, which is now, acting on this subcategory because T is isomorphic to the shift, admits an induced D plus 2 undulated category structure. Can be given explicitly. This consists of all splicings of triangles that have all the terms that live along the spine. So something like this, where all the terms live in the additive closure of T. And using these results, one can show the following proposition that was actually observed first by Bougat in 2012 in the algebraic setting, by Hanihara in 2020 in the case D equals to 1, and by Arun Chan, Eric Darko, and Osamu Iyama. I lost track of this one. I think it was published in 2024. Yes, which is that if T in T is this at closer tilting. So now I gave you maybe a sketch of how you would prove it in a different way. Those proofs are a little bit between different and same. I don't want to unravel now the direction. If T is this at closer tilting, then its endomorphism algebra is twisted equals to periodic, because the additive closure of T under the Yoneda embedding identifies with the category of projective modules over this finite dimensional algebra, which admits a D plus 2 angulated category structure, and therefore is twisted D plus 2 periodic. So,
what did you mean by the bracket at T in the previous one? The bracket at T and the shift that they took?
Yeah, so a triangulated category. So this is still very non-Heidegger structure-like.
Yeah.
So a triangulated category is an additive category with an autoequivalence plus a triangulation, right?
Okay.
So here, this is the base additive category. This is the base automorphism, U1 or autoequivalence. And then there is a class of D plus 2 angles that satisfy the axioms of D plus 2 angulated category that involves now this suspension. Okay. Now, just to finish, so what we have a right to is the following. Well, we do have a statement that says endomorphism algebras of these at closer tilting objects are special. Yeah, so they are twisted D plus 2 periodic. So now one can ask oneself about the converse. Yeah, can you? So this is now a sort of basic say question for representation theorists. We have a class of finite dimensional algebras. They arise as underived endomorphism algebras of generators of a certain kind in triangulated categories. And then you can ask, can all of them be realized in this way? Yeah. And in our setting, it's also very natural to ask, can T always be chosen to be algebraic, meaning coming from DG category world? Yeah. And well, this is what the lecture series is about, to tell you. So I will start next time with the main theorem or theorems and explain, in which sense this implication can be reversed, and then we will explain why you need to work with Heidegger structures to reverse the implication. So we need to now, given a twisted periodic algebra, construct a triangulated category with the decent cluster tilting object such that something that comes back. Yeah. And I will try to explain some of the proof of that theorem and some of the main ideas that go into it that use ideas of homotopy theory, because I think this is what maybe everybody here is interested about. And how it maybe for many of you, I know the theorem in itself is not necessarily so interesting. Maybe you are not previously interested in this kind of question, but at least you hopefully will be able to see how ideas of homotopy theory can be used to solve some kind of, I mean, so far it's all about this statement of some finite dimensional algebras. Yeah? So it's very elementary in some sense. But it turns out the proof is, as far as we know, no. Okay, thank you.
Thanks. Are there questions?
Can I push you on that last comment a little bit? Higher things and homotopy theory. So there's the Schwede-Shipley recognition theorem, which seems to play sort of the shadowy role here, which says that if you have a stable category in a single compact generator, then it's equivalent to modules over the endomorphism ring spectrum. How would you think about it if you want to phrase this in terms of stable categories? How would you think about your story?
Well, I would use first of all a precursor of the Schwede-Shipley recognition theorem, which is the Keller recognition theorem for algebraic compactly generated triangulated categories, where instead of getting, in the case of this single, so of course I will assume T is algebraic, so enhanceable if you want to a stable infinity category which is linear over my ground field. Yeah, that's the setting I want to be, but I want to use DG algebra. Then in that setting, I will know that T will be equivalent to the perfect derived category of the derived endomorphism algebra of T. That is now not a ring spectrum, but if you want, it's an HK algebra spectrum, but I will want to have modeled this as a DG algebra. So that will be the first thing is, of course, that we will turn this statement about understanding certain DG algebras. So I want to construct, so maybe I say this since you asked it in short. I want to realize this as the cohomology of a DG algebra. Will turn out that the assumptions on T are such that just by knowing this and sigma, I can actually know as an algebra what the cohomology will be. Yeah. So at this underlying level of this graded cohomology, I know the algebra I want to get, and now I want to realize this DG algebra. This graded algebra as the cohomology of a DG algebra. This is of course very easy because I can just put differential equals to 0. Yeah? But I want to relate the property of being this at closer tilting to this DG algebra. And this is the whole point. Yeah? So that's how, so you could do this also with ring spectrum, and conceptually you should just think in terms of HK algebra spectrum, and then this would be the stable homotopy groups. This form a graded algebra over this field, because everything is HK linear. Now the question is, how do you guarantee that this other derived algebra, yeah, has this good generating property? And this is what the whole lecture series will be about. Thank you for your question. There is, well, sorry. You want to ask first, or? Okay. He says you can ask first.
At the beginning, that the results you were showing led to Auslander writing theory. Can you explain a little bit more why?
Yes, so the slogan is AR sequences correspond to minimal projected resolutions of simple modules. Let me write, I've done the writing sequences over lambda correspond to minimal projected resolutions of simple gamma modules of projected dimension equals to 2. Which was the maximum possible according to the definition of this algebra as gamma. And then now you can ask yourself, what if your algebra has not finite type? Then you consider simple modules. So gamma is some kind of avatar for the whole module category. So when this is an additive generator, I can collect the information of all this category into an algebra. But when it is infinite type, I can't, because I have infinitely many decomposable objects. So you can look at modules over that category as if it was an algebra. And then develop, this is what's called the functorial approach to representation theory to understand this kind of, how to go from this to the general case. I mean, of course, you need to understand that this is interesting to do, at least one last class of short-term sequences. That's obviously where we started in the 70s. There was a question on the back.
Can you give an example of the twisted periodic algebra?
Yes, so dual numbers.
Okay.
Yeah. That's maybe the fastest.
T equals 1?
Yeah, and then the periodicity repeats. So maybe in characteristic 2 is periodic for all periods.
Okay, so do you have that?
I can also ask this, but
Yeah, if you maybe
I think
if you want to finish, that's also
I
fine.
mean, I think we have that. I mean, it's very different. We don't have anything else.
okay, so I'm also asking for an example. If you have a recommended example, think of where to find these DC cluster objects. For instance, for D equals 1, this should be an additive generator of the triangle.
Yeah, I mean, stable categories of self-injective algebra as a finite representation type would be a basic example. Cluster categories of thinking type, where finitely many composables. Some stable categories of Cohen-Macaulay modules of finite Cohen-Macaulay type. Of rings of, sort of Cohen-Macaulay rings, finite Cohen-Macaulay type, things like this. This would be for D equals to 1. For higher D, I will explain maybe more. Well, in general, I will give a list of examples of interest without explaining what they really are, but maybe so that you see that there are many examples in this time.
Okay, so let's bring Gustavo, yeah?